by Terahertz Communications in the 6G era. And after that, I will give a very brief review about the properties of terahertz channels, as well as the progress in terahertz device technologies. I have to say that I'm not an expert in terahertz channel modeling and device technologies. I'm not an expert in that, but as a scientist doing physical layer design, it's better and it's a must for us to know the basic knowledge about the channel properties, as well as the properties and the constraints of the terahertz devices, such that we can perform feasible and successful design. And after that, I'm going to introduce two pieces of my recent works in Terahertz Com. One is about system level performance analysis, and one is about hybrid beamforming. And in the last section, I will give a few open problems and challenges for Terahertz Communications. So here is the structure of my talk today. So let's start with the 6G era. As you can see from these slides, this is our world. And as you can see in this world, and over the past few years, over the past decades, we can see we are interconnected with the people from other continents, from other countries. And if we look a few years later, say next 5 years, or even next 10 years, definitely we would like to build up the networked society or the highly connected network society, such that each person of us can connect with any other person, any other device, any other city, any other area. We want to build up this kind of connection to form our society. So in this case, we would like to say that in today's and even tomorrow's network society, we definitely need different kind of connections to move forward. And over the past decades, it's very proud to say that wireless communications have fundamentally transformed the way that we access, exchange, and gather the information from different properties. And because I believe that most of the audience today come from a communication background. So I firmly believe that you have known that people have witnessed the evolution of wireless cellular networks from 1G to 2G to 3G to 4G. And now, as we have mentioned here, the 5G systems are currently being deployed worldwide, including Australia, and they offer significant advancement over the 4G LTE system. So this is good. But our evolution would never stop. If we look at the current 5G and compare it with the initial premise, somehow we can see a slight misalignment or gap between our expectation of 5G and what the real, the practical 5G, which is produced by the industry. Because if we consider the initial premise of 5G, it is used to be considered or proposed as a true carrier of the Internet of Everything services. But this initial premise has not been realized yet. Although we firmly believe that the 5G system in the near future, they can support basic IoE services, they can even support basic URLC services, but the true promise of 5G has not been realized. And at the same time, I would say it is a question mark for me, and maybe for a lot of other people. It is a question mark for us that whether 5G can successfully deliver the unprecedented Internet of Everything applications. For example, we may build up the extended reality services to different industries like telemedicine, haptic, the connected vehicles and UAVs. We are not sure, and it's a question mark for us that whether 5G can deliver that. Because if we consider these applications, if we want to successfully deliver these applications, we would need a wireless system which has some very advanced capabilities. For example, we may need the wireless system to deliver the ultra-high data rate, the ultra-high reliability, the ultra-low latency, and support a massive number of different type of devices, including human-type devices, machine-type devices, and support high-quality uplink and downlink transmission. At the same time, we may also look at or need a wireless system which can have an end-to-end design, which have jointly considering the functionalities, not only including communication, but also including control and computing and other functions. So these applications are actually beyond the capability of 5G. And in this case, I believe that the vast majority of the communication society believe that we need a new and cutting edge 6G wireless system to serve our society for 2030 and beyond. And if we consider that, and what would be the vision of 6G? I would like to share my viewpoint is that the 6G have been proposed, but what will be the true 6G? This is still under discussion and under development. And if you look at the recently published, like magazine papers, news articles about 6G, the viewpoint from different people, from different research groups, from different industries, they are somehow different. But if we try to gather this kind of different perspectives together, we can find something in common. The first thing we found something in common is that if we look at 10 years later, we would like to see a ubiquitous intelligent information society. And typically we agree that this society would be highly digitalized, this society would be intelligence inspired, and this society would be massive data driven, and that would be supported by the near instant and unlimited full wireless connectivity. We want to use wireless connectivity to support this society. So I would say, compared to other techniques, 6G would be a key enabler to achieve this blueprint. And by doing so, the 6G would be expected to provide a large number of benefits that we cannot currently realize by using 5G. And we have provided this kind of, the gather of the information here. For example, 6G will connect everything and provide full dimensional wireless coverage. The 6G would serve as a autonomous and serve as a three centralized system where they focus on the user's requirement, focus on the data, and also focus on the content or the value of data. And at the same time, 6G would integrate different kinds of functions together, such as communication, computing, caching, sensing, control, positioning, navigation, imaging. And this kind of integration will help us to support full vertical applications in different environments. And 6G may allow us to use multiple ways to communicate and interact with smart terminals. And at the same time, 6G is highly anticipated to gain a certain level of intelligence and has the capability of self-awareness, real-time dynamic analysis, and adaptive risk and confidence evaluation. So these are the visions or the targets or benefits which would be provided by 6G, which come from different people and different industries. And based on that, people are trying to gather the requirements of 6G, and based on these requirements, people are trying to figure out the user cases that can be realized by 6G. So from this figure, again, this is just like a figure come from a recently published magazine paper, we can see that the 6G would be able to support the very high data rate, which may be higher than 1 terahertz bits per second. At the same time, the 6G may be able to support the very low latency, maybe even lower than 1 millisecond. And 6G would like to support a huge number of connectivity and achieve a super high or ultra high reliability. And based on this, we can see these performance metrics or these key performance indicators, they will be really, really hard to be achieved by the current 5G technologies. And with achieving these key performance indicators, 6G would help us to realize some very promising applications. For example, if we have a very high peak rate, we can realize the extreme mobile broadband, and this will help us to bring something like holographic communications, VR and AR-based sensing, remote learning, and tactile internet. So these kind of applications will be realized by 6G. So based on all this kind of information, I know I may spend a bit more time on that, but I would like to say 6G is something like we really want to put our research efforts on from now on, because we want to build up something which can be used in 10 years later. So in this case, it's happy to see that the research on 6G has been commenced worldwide. For example, if we look at the International Telecommunications Union, they have had a focus group for the technologies for Network 2030. And if you are interested in what they have proposed or what they have written in their like the technical report or white paper, please feel free to look at their website. They have really provide some interesting things. And then in terms of research, if we look at worldwide, for the European Union's Horizon 2020 has recently supported a new project led by Nokia. They are aiming to develop key technologies for 6G. And then for the United States, the FCC has opened the experimental spectrum license for Terahertz Communications test for 6G, and that is directly to, as I mentioned, directly relevant to Terahertz Communications. And apart from that, if we look at Asian countries, China has launched a big project for 2030. Japan has invested almost like 500 million for 6G research and development. And even if we look at South Korea, if I remember correctly, they mentioned that they want to release the first 6G trail in 2026, which is quite promising. So before we move forward, I really hope that in Australia, like we, as the researchers in communications and signal processing and networking, is something like we can devote our efforts in the 6G research. And it's better that we can form a somehow like an alliance such that we can get some support from the government or from some sectors. I think that would be much, much better for Australia to move forward. So in terms of the 6G, we have mentioned that 6G is a must. And then let's going back to the role played by Terahertz Com for 6G. So why is Terahertz communication important for 6G? The first question and key question we want to ask here is that, can the current frequency spectrum satisfy the demands of 6G wireless systems? And my answer is no. My answer is no. I mean, the current frequency spectrum is really, really hard to satisfy the unprecedented performance metric of 6G systems. And in this case, at least from the frequency perspective, we need to explore the benefits of Terahertz communications. And typically we consider the Terahertz communications is operated at the terahertz band, ranging from 0.1 terahertz to 10 terahertz. And when we talk about the Terahertz Com, it is quite neutral for us to consider that, okay, the terahertz band is higher than the millimeter wave band, but it is lower than the infrared and visible light band. So what is the unique benefits of Terahertz communication compared to millimeter wave and visible light? So from my perspective, I admit that millimeter wave has been officially adopted in 5G. For example, I think in the United States and some other countries, they have provided the 5G service based on the carrier frequency of 26 gigahertz. But despite this prospect, it is still very difficult for using millimeter wave to support the terabit per second data rate. It is very hard. And at the same time, if we compare Terahertz Com with visible light, I would say the visible light communications is somehow relatively mature. But if we compare terahertz signals and optical signals, we can see that first, terahertz signals are not affected by some factors that affect optical signals, such as the ambient light, the atmospheric turbulence, like the things I have mentioned here. At the same time, we know that the visible light communication, they have the super narrow beam properties, such that they need a dedicated pointing, acquisition, and tracking to guarantee this precise alignment. And apart from that, the visible light communication may not be the best option for uplink because of human eye sensitivity. And also, we know visible light is always very vulnerable to different types of blockage. So in this case, we would say that the research on Terahertz communication is important, it's pivotal, but definitely from my perspective, we doing research on Terahertz Com, but it does not mean that when the Terahertz Com comes to the real life, we want to use Terahertz Com to replace millimeter wave, to replace visible light in everywhere. It's not something like that. We want to enhance the wireless availability by using, say, sub-6 gigahertz, millimeter wave, terahertz, and the visible light in a heterogeneous setup, just like what we are doing now by jointly using the millimeter wave and the sub-6 gigahertz. That's why Terahertz Com is important. It has benefits compared to millimeter wave and the visible light communications. And based on that, we know the terahertz spectrum can provide the huge available bandwidth, such that it can tremendously enhance the capacity of the current wireless system and can have the potential to help us to achieve the terabits per second data rate. And based on that, once these super high or ultra high data rates can be supported, the Terahertz communication can support something like the Terahertz Wi-Fi or WLAN system. They can use to support the Internet of Things in the wireless data center, like to build up the communication between data centers. They can use to support the access backhaul in the wireless networks, and even they can use in the space communication to support the inter-satellite link, something like that. And apart from that, we also know that the Terahertz communication has a very small waveform, such that the device and antennas will be of small size. And in this case, Terahertz communication can also be used to support something like the wireless networks on chip communications, as well as the Internet of Nano Things, such that they can work on a very small scale. And then based on the huge available bandwidth of the terahertz spectrum, we can also use terahertz to produce the joint systems which combine communications and the sensing and the imaging and the localization, something like that. So these are the potential application areas of the terahertz communications. And based on this, we would like to start the terahertz communication research. And from our perspective, we mainly focus on physical layer or even macro layer or network layer design. But before that, it will be good for us to know the basic properties of terahertz channels and devices. So let's look at the brief review information about terahertz channels. The terahertz channel modeling and characterization is quite important because it helps us to understand the terahertz spectrum. At the same time, it lays out the fundamentals of our design of the communication strategy and networking protocols. So what would be the most important properties of terahertz channels? So let's start with the large scale propagation. For the large scale propagation or terahertz propagation, it is affected by two phenomena. One is the spreading loss, one is atmospheric loss. The spreading loss typically increase cogetically with the frequency. And according to some demos or some test result, the free space loss of a 10-meter terahertz link may reach 100 dB, which means the space loss is very large. At the same time, apart from spreading loss, because we know spreading loss almost exists in different kind of microwave or millimeter wave transmission. But another property we have to be aware of is the atmospheric loss, or specifically is the molecular absorption loss. In terahertz communications, molecular absorption loss is caused by the polar gas molecules in the medium, and these molecules may absorb terahertz energies. So this is quite interesting but unique and important property that we have to consider in the large scale propagation of terahertz communication, because both the spreading and atmospheric loss affect the terahertz wave propagation, and they will lead to the distance and frequency dependent spectrum windows. So the spectrum windows is the property that we have witnessed in the terahertz propagation, and they depend on the distance and the frequency. So how it looks like, here I provide a figure. So in this figure, you can see that we plot the path loss, which given in dB, against the frequency, which ranging from somehow 0.1 terahertz to 1.5 terahertz. So we can, and also we plot the distance, we plot the path loss against different distance, like 0.1 meter, which is the path loss is relatively low, which makes sense, right? And then we also plot the distance at 1 meter, 10 meter, and 100 meter. And we mentioned that by being affected by the spreading loss and molecular absorption loss, the terahertz propagation, they have this kind of path loss peak. When we say path loss peak, for example, if you look at some frequency around 0.6 terahertz or around 0.8 terahertz, these are the path loss peak. The path loss peak means that the path loss is super severe. So it definitely is not good to send our terahertz signals along this kind of frequency, because the path loss is very severe. And between this path loss peak, we have some relatively flat the spectrum response, and this is the window that we talk about. As we mentioned here, you can see the spectrum window depends on distance and depends on frequency, and we try to use this relatively flat frequency response to perform our transmission. For example, from here to here and a bit above like 1 terahertz. So these are the flat frequency response that we can use to perform the transmission. So this spectrum windows is something very interesting in terahertz channels, and this is something that we have to consider when we perform the design of terahertz communication systems. And apart from that, we also know that for terahertz multipath propagation, we can easily observe the clustering effects and the channel sparsity. For example, if we look at the angle of departure and angle of arrival, we can see the channel sparsity. Then these are mainly caused by that. In terahertz propagation, there are really a very limited number of reflected passes. So for terahertz propagation, typically we consider the line of sight are the dominant link. And at the same time, we know that terahertz propagation can be easily blocked by objects, especially compared to millimeter wave. And apart from that, I also provided some information about shadowing, fading variance, and diffraction effect. But as we mentioned, mainly when we design the terahertz communication systems, we consider the clustering effect, the channel capacity, the dominance of line of sight, as well as different blockages. So these are the key key factors that we consider when we perform the design. And then apart from the channel modeling, another thing is for us to get some knowledge is terahertz device, like the terahertz transceiver and terahertz antenna. Again, I'm not an expert in this area, so I just try to provide some basic understanding, and I hope they are correct. And conventionally, when we try to generate the terahertz signals, we have witnessed the lack of compact high-power terahertz signal generators and the high sensitivity and the low noise terahertz detectors, and they are the hurdle to realize terahertz communication. But over the past years, we have seen some very promising and recent advancement. Of course, they are doing from different technology paths, but they are jointly working to try to fill in this terahertz technology gap. For example, we may consider electronic technology. The electronic technology is something like they try to generate the terahertz signals by using the up conversion from the lower frequency signals. Like if you have a millimeter wave frequency and then you do the up conversion, you raise the frequency from relatively lower millimeter wave signals to terahertz. And then another approach is photonic technologies. Photonic technologies is something which generate the terahertz signals from another way that they consider the optical signals, and they doing the down conversion to drag down the frequencies. So these are the two conventional or traditional methodologies. And apart from that, there is also another technology which is the plasmonic technology. For example, some people have investigated the use of graphene to do to produce the terahertz transceiver and antennas. And these devices are intrinsically small, and they can effectively operate at terahertz frequencies. And by using the hybrid graphene and semiconductor device, we can directly generate the terahertz signals, which is good. So based on these terahertz device technologies, and we can see that there are some different ways to generate the terahertz signals. And then when we perform the design, and especially when we try to engineer our design, it's better for us to consider this device constraint and then to align our design with the properties or limits of this device. So this is the main purpose for us to understand the terahertz device technologies. And after we're briefly talking about the terahertz channel and the device, let's look at the physical layer design, which I'm going to introduce two of my works. For the physical layer design, we know that a major challenge for terahertz communication is the distance limitation. And this is caused by the very high propagation loss, and this has been talked before. And at the same time, when we perform design, it is better for us to effectively exploit the terahertz channel characteristics, such as the spectrum windows that we have introduced before. And based on this, by summarizing the main research directions in Terahertz Communications, I have listed something here. So over the past few years, the main research directions in Terahertz Communications, including something like channel measurement, modeling, modulation and waveform design, coding and error control, design of massive MIMO or even ultra-massive MIMO with signal processing such as hybrid beamforming, system level analysis, secure and covered communications, joint communication and other functions like sensing and imaging. At the same time, if we want to build up the terahertz network, we need to look at the MAC layer control as well as the networking protocol design. So these are the main research directions of terahertz communication over the past years. And definitely I know there might be other research directions that I haven't included here, but I would say the research on terahertz communication is booming. So that is why I firmly believe the research on terahertz com is very beneficial. And then in this work, I'm going to introduce two of my works. One is on system level performance analysis, and one is on hybrid beamforming. So in terms of system level performance analysis, I would like to focus on my journal paper published in GSAC, in which we focus on coverage analysis. So what are the contributions in this work? We provide some novel coverage probability analysis of downlink transmission in a 3D terahertz communication system. And in this system, we consider the unique propagation properties at terahertz band. We consider the effect of 3D directional antennas. We also consider the joint impact of 3D blockage caused by three things: the user itself, moving humans, and wall blockers. So these are the system we consider here. So in order to perform the coverage and probability analysis, we build up an analytical framework, and we examine the regions where the dominant interferers exist. And later on, I will explain what the dominant interferers are. And we also validate our analysis and provide some insights. Particularly when we show that the interference in terahertz communication still play a significant role, such that we have to try to provide as accurate as possible way to evaluate its impact. So these are the main contributions of our journal in the system level performance analysis. And then let's look at the system model that we consider here. So this is our system model. So from this figure, you can see we consider a 3D model. So there is a user, and we have a lot of APs. They are mounted on the ceiling, and we also have some blockers. So this is the model. So in this system, we consider the downlink transmission from the AP to a typical user. So we assume that the typical user as the UE0, and this user is at the center of this indoor environment. It has a height of HU. And at the same time, we assume all the terahertz access points, APs, they are mounted on the ceiling with the height of HA, and they follow a Poisson point distribution. And then apart from this UE, we also assume that there are other UEs distributed in this environment, and each AP associates with a single UE and transmit to this UE. I mean, although in this figure, we did not plot or we did not show these UEs in this figure, but we do consider the existence of UEs, and each AP associates with a UE and they transmit, such that for this typical UE, it associated with its own AP, which is AP0. But at the same time, all the other APs, they act as interferers. That is why we have to evaluate the interference caused by other APs. But then we want to ask, whether all these other APs cause interference. The answer is not, because we also consider blockage effect. So in this figure, we consider three blockage effect. One is a self-blockage. So self-blockage means the blockage caused by the user itself. Suppose that for example, the device is here held by this person, then we can see that some APs behind him, these APs are blocked by the user itself. So this is a property in terahertz communication. This means the terahertz signals can be blocked by the user itself. And then the second type of blockage is dynamic human blockers. So here we use this rectangular to simulate or to approximate this dynamic human blockers. Again, they follow a PVP distribution, and we also use the random direction model to model their mobility. And we also have these wall blockers. The wall blockers is dynamic. So this is our system model. So we can see the 3D propagation, and then we can see the 3 type of blockers. And based on this case, we want to evaluate the coverage probability. But before that, we want to show 2 models. One is antenna model, one is propagation model. For the antenna model, we consider the 3D antenna beams are used at both the AP and the users. So this is the illustration of the 3D antenna model, where we use the pyramidal shape to show the main lobe of the antenna beam, and then we use this this ball shape to show the side lobes of the antenna beam. So we can see this is a 3D because we can see the horizontal beam wave and the vertical beam wave. And then the antenna gains, by using some antenna propagation theory, we model the antenna gains in these 2 equations. But definitely our analysis is also valid if we consider another type of antenna gains. And then for the propagation model, we mentioned that in terms of terahertz communication, the signal propagation at the terahertz band is impacted by 2 things. One is spreading loss, and one is molecular absorption loss. And based on this, if we define dxij as the 3D distance between the AP and user, then we see that the received signal power at the user is given by this result, where we use the power to this factor to denote the spreading loss, and then we use this exponential function to denote the molecular absorption loss. And definitely the molecular absorption loss depends on distance and the frequency. This has been shown in one of our previous slides. So this is the propagation model. And based on this, we would like to emphasize that due to the high reflection, diffraction, and scattering, we only focus on line of sight terahertz link, and we try to ignore the impact of non-line of sight link, because in terahertz communications, especially when we consider this system level analysis, the impact of non-line of sight link is very, very minor compared to the line of sight link. It may be only like 1% of the impact of a line of sight link. That's why it is reasonable to ignore that. But of course, if you want to consider that, that is also fine. This will give you maybe a better accuracy, but a lot of mathematical complexity. So this is the antenna model and the propagation model. And based on that, we first try to analyze the impact of blockage. So in order to do that, we analyze the line of sight probability of the AP to user link when we consider both human and wall blockers. So this is the equation. So here, I just in this work and in the following work, my intention is just to provide some key results without talking about the derivation results, derivation details, or algorithm details, because if anyone is interested in that, please feel free to read our paper. But for the sake of presentation, I prefer to omit that. So going back to our work, we first derive the line of sight probability. So this is given by this result. This line of sight probability is caused by the line of sight probability in the presence of human blockers and the line of sight probability of wall blockers. And we assume human and the wall blockers, they are independent with each other. And then we also want to investigate the impact of 3D antennas that we have considered in the previous slides. So in order to investigate the impact of interfering AP on the aggregated interference at the user, we try to determine the heating probability. So the heating probability is defined as the probability that the signal corresponding to the main lobe of interfering AP reaches the user. So this is the heating probability. So the heating probability is the probability that the signal comes from the main lobe from an interfering AP and reaches the user. So this is the heating probability. And considering the 3D model, this probability is given by this equation. And we can see it consists of two parts, horizontal heating and vertical heating. For horizontal heating, it can be easily found because there are a lot of, the coverage probability analysis based on 2D model. So for 2D model, we can directly find the horizontal heating probability. But for vertical heating probability, we have to derive it from scratch, and this is the result. By combining these results, we have the heating probability. And this heating probability will be used in the following analysis. So after these two results, we proceeded with the coverage analysis. In our system, the coverage probability at the target user is defined as the probability that the SINR of this user is larger than the predetermined threshold. So in this case, mathematically speaking, it is given by the product of two things. One is the line of sight probability. One is the probability that the SNR is higher than the threshold when this link is line of sight. So it is given by the product of these two probabilities. And as we mentioned before, considering the 3D model, 3D antenna model, we find that the conventionally used Laplace transform-based approach is not attractable. And in this case, we have to find a new way to analyze the impact of interference. Some papers or some existing studies, they analyze the impact of interference using average interference. That means they try to calculate the mean value of the interference and they use it always. But in our paper, we try to use another way, which is a more accurate way to deal with the interference, where we use the dominant interference analysis. So by doing this analysis, we partition the APs, which contribute to the interference, into two sets. One is dominant interference, one is non-dominant interference. And an interference is defined as the dominant interference if it causes outage by itself. So this is the definition of a dominant interference. I mean, if an interference can cause the outage by itself, it is a dominant interference. And of course, the interference that cannot cause the outage by themselves is the non-dominant interference. And based on this, we will transform this line of sight, this probability that SNR is higher than the threshold, as the probability that no interference is dominant between the link of AP0 and UE0. So this is how we do, somehow like a transformation to simplify our analysis. And based on this, again, I try to ignore the derivation details, but the coverage probability can be ultimately derived in this equation. And for this equation, we consider the average number of near dominant interference, which is given by this result. And we also have the average number of far dominant interference, which is given by this result. And the detailed derivation for these two results have been provided in the paper, and they use the heating probability that we just introduced before. So here is the coverage probability, and this is the key result. And then definitely we want to use numerical result to show the benefits. So here we plot the coverage probability against the horizontal distance between AP0 and UE0. And we find that our analysis, like for example, our analysis, this black curve, they somehow well matches the simulation result, especially when the distance is low and medium. We can see from 1 meter to maybe 8 meter, even 9 meter, the analysis and the simulation match very, very well. This shows the importance of our 3D analysis, because if we consider 2D analysis, this blue curve does not make sense. And if we consider some existing analysis, this green curve, again, it has an overestimation of the coverage probability. And then we also consider another case, like the coverage probability against the horizontal distance, but this plot is against different transmitted power and the antenna gain at the AP and the antenna gain at the user. So we can see that in this figure, we can see that the coverage probability improvement brought by increasing or changing the antenna gains is much higher when we have a higher or larger distance between the AP and the user. So in this case, we also show that it is better to increase the antenna gain at APs rather than at the users. So this is our key results. So this is what we have been doing for the system level analysis. And then in the following, maybe I need to talk a bit faster, that I just maybe use 5 minutes to talk about what we have doing for the hybrid beamforming. For hybrid beamforming, we know that the hybrid beamforming is a promising signal processing technique for Terahertz communication, because we always use Terahertz, like massive MIMO in Terahertz communication. So compared to the fully digital beamforming, which has a higher power consumption and higher hardware cost, and comparing to analog beamforming, which has a lower complexity but only supports one data stream, the hybrid beamforming strike a balance. It uses a limited number of IF chains but achieve a comparable data rate. But of course, in the design of hybrid beamforming, we need to consider the specific property of Terahertz communications, such as the channel sparsity, the low spatial degree of freedom, and the spectrum windows. We have to consider this kind of result. So for hybrid beamforming, we produced a paper, we published a paper last year. And for this paper, we designed the hybrid beamforming for Terahertz Com, where we consider a multi-antenna base station communicates with a multiple antenna user. The base station employs sub-connected hybrid beamforming and the multi-carrier modulation. We also consider the wideband terahertz channel with molecular absorption, high sparsity, multipath fading, and carrier frequency offset. So in this case, we consider two beamforming schemes, and we will show the bit details later. For this, so this is a system. This is the base station that we consider in our paper. So in this paper, we consider Terahertz communication from a multi-antenna base station to a multi-antenna user. And as we can see here, the base station employ the sub-connected beamforming, like each RF chain connects a sub-array. And so the total number of base station is given by NRF times MT times NT. At the same time, we assume that user only employs one single RF chain with one sub-array. So this is the number of user antennas. And we also consider that the base station adopts the multi-carrier modulation to transmit signals such that they employ K non-overlapping subcarriers to perform the transmission. And then in this work, we explored the transmission window. So we focus on the absorption-defined transmission window from 300 to 450 gigahertz. And here is our modeling of our channel that we consider a dominant line of sight and a limited number of non-line of sight arrays. And for the terahertz propagation, the path gain consists both of spreading loss and the molecular absorption loss. So here is the channel we model, and based on this model, we want to use this channel to formulate our problem. And of course, as we mentioned, we also consider carrier frequency offset, because in multi-carrier systems, the accurate frequency synchronization will be very challenging. So we consider this CFO, which is typically caused by the misalignment in the carrier frequencies. So based on this, we formulated the received signal. And for the received signal, we see that the received signal contains not only the useful signal, but also the interband interference caused by the CFO. So this is the interband interference. So this is something we want to try to deal with in the beamforming design. And then based on the received signal, we have formulated the average achievable data rate, and the SNR can be directly expressed based on the received signal. And our job in the beamforming design is to find the V, which is the analog beamformer at the user, W, which is the analog beamformer at the base station, and FBB, which is a digital beamformer at the base station. We want to perform the design to maximize the average achievable data rate. And based on this, in this paper, we propose two hybrid beamforming design. For the first beamforming design, it is two-stage one. So for the first design, for the analog beamforming, we design a beam steering codebook searching for the analog beamforming. And then for the digital beamforming, we use the regularized channel inversion to eliminate the interband interference caused by the CFO. So this is our first design. And for the second design, we try to avoid the exhaustive search in the analog beamforming in design one. So in this case, in the design two, we first jointly design W and V to maximize the desired signal power. But in this design, we try to perform the design based on some simplifications. And then for the digital beamforming design, we decompose that into two matrices. One is composition metric, one is RCI metric. So the composition metric is a new design in this design, and this is used to compensate for the performance loss of the obtained analog beamforming from stage one. So this is our roughly like the very brief introduction to the idea of these two designs. Again, we provided the formulation and design details in the paper, so please feel free to look at the papers to see the details. And then for the results, we compare our proposed results with the existing result and the fully digital performance. So it's good to see that our eigen-based hybrid beamforming, which is our design tool, achieves a comparable performance to the fully digital beamforming, which is very good. And then it outperforms our codebook-based hybrid beamforming, which is the red curve. The red curve is our design one. So design two, design one. So we show there is a performance, we show that the design tool achieves a comparable performance to the fully digital one, but with a lower complexity. And then for the design one, again, the performance is not that bad, it's still acceptable. So this is the quick introduction about our second work. So in the last, I would like to show some open problems and challenges for Terahertz communication. So Terahertz communication is a hot topic, we know that. So there are some numerous major challenges for Terahertz communication. For example, in Terahertz device, Terahertz modulations, Terahertz antennas, and I would like to leave these challenges to our colleagues and collaborators in other areas. I'm happy to do that, but for our perspective, we still have our challenges. For example, I have listed something from the communication theory and the signal processing perspective. For example, we always want to build up an accurate and generalized framework to evaluate the performance. We want to design the transmission and reception based on the hardware constraint. We want to explore the practical characteristics to design the hybrid beamforming, such as some new hybrid beamforming architecture, some other quality of service targets, some multi-connectivity design. And apart from that, we want to introduce the artificial intelligence into the design. We also want to perform the joint design of Terahertz Com with other promising technologies. For example, intelligent reflecting service that is quite useful to compensate for the performance of Terahertz Com. And lastly, if we want to perform the joint design of communication and the other functionalities, we need the beam management and the spectrum administration and the medium access control. We need that. So here are some future directions, a very brief introduction about future directions in the Terahertz communications. So I think this is the last slides of my talk today. And here's the reference I used for this talk, and please feel free to look at them if you want to get some basic idea of the Terahertz communication. And I'm sorry, my presentation is longer than what you thought. And lastly, I would like to acknowledge my students and collaborators in Terahertz communications. So this is the end of the talk. Thank you very much.